So our goal right now is to work with the trajectory. So we're going to have to set a bunch of values. We're going to set v naught equal to something. So this is roughly the design that's on that terrifying leaf that's on the last page. So about 3 meters high was the height of that berm that they went off of. Sorry, that's y naught. V naught, 20 meters per second. And last but not least, theta naught. I have to write theta naught, unfortunately. Will be 30 degrees. All right. So in any of these problems, we define the numbers, the constants, the values that are known in front. Might as well put them at the top. And then we write our code below that. So the next thing to do is define our x values. Let me just go back to our question here. Right, we're going to choose the x interval so it shows the impact point. Well, we don't really know what that is. So let's go for 10 meters and see what happens. 0 to 10. I hate this keyboard. All right. So what we're going to do is generate a sequence of x values like we did in the first week. Hey, x values from 0 to 10, 100 of them exactly. That should be enough for any graph. And then our y values are going to be defined by that formula. So we literally copy in that formula. Tan of theta naught times x plus minus 9.8 over 2. And then it can be 1 over, let's do it this way. Okay, so we can divide it by that. How about we just divide it by that? Cos of theta naught squared and a v naught squared. And all of that times x squared. I think that's our formula. I'm just going to flip back for 1 sec and go to our formula. That's the bulk of it. So yes, comments or questions before we start running it? Shouldn't it be tan? Excellent point. What is tan used by its natural inputs? Radians or degrees? Radians, right. What do we have? We have degrees. So absolutely. If we want to use degrees, that's fine, but we better tell MATLAB that we intend to do that. So in the other one, cos, yeah, there's a cos as well. It has to be cos d. Absolutely. Any other known problems before we try to run it? Recognized? Yeah, go ahead. Absolutely. We've got multiplications and we've got some matrices. So if in doubt, just put a bunch of dots and then see what happens. Honestly, if they're scalars, it doesn't matter. And there's no way we want matrix multiplication here. So putting a bunch of dots is not a bad thing. So we'll try this, and then we'll plot x and y. I'm going to add one thing at the top here, which is close all. I'll leave it space there. What does that do again? Closes all your windows. Well, not all of them. All your graphing windows, though, yes. So what that does is every time you run the program, MATLAB goes, oh, I don't have a graphics window. I better pop your graph up in front of you so you don't have to go hunting for it behind your main window. So that's why I put that in there. And if we run it, we will see, hopefully, a screen pop up in front of us. Ta-da! All right, cool. So that is our trajectory. We apparently need to go further. We're only seeing the first part of it. So how far, just looking at that, do you think we should go out to? Speculation? 40. Lovely. 40 meters. No, that's 50, sorry. Definitely not 450. Yeah. One more time. There we go. OK, that's actually surprisingly close. So there's 0. Let's go to 45 or something, just so we can see everything for sure. All right, so you can already feel some little element of guessing and checking. How far does this go? I don't know. I have to plot it and then see. That is a very common theme for solving nonlinear equations, is to plot it, get an idea, and then use a tool to refine your answer. Next step is to actually highlight what the point we're interested in, which is that impact point down here at 0. Now, you can do it manually, but I think it behooves us to actually plot the line for the ground. That'll make it easier to see things. All right. So one of the nice ways to do this would be to make an x ground be 0. There's a few different ways to do this. But the maximum of our x values is a nice place to stop. So we're going to make a 2-point line. It's a straight horizontal line. It'll start at x equals 0 and go to the maximum of whatever we plotted with. And the y values will just be 0 and 0, so it's height 0, and it'll connect that dot. So we're going to plot that, x ground and y ground. And we'll plot that in black to make it kind of obvious. Comments or suggestions before we press go on this one? Yes? Absolutely. What's going to happen if we run this right now? Just to remind you, we are going to get exactly one black line. That's it. Because when we said plot the second time, plot by default will wipe your old graph out and put the new graph up. It assumes that's what you want. In this case, we have a little more subtlety in mind here. So we're going to have to put a hold all or hold on, whatever your preference is. And that will put the first graph and then says keep this first graph on the screen. Any other graphs keep showing up on the screen. And there we get our desired graph. Fantastic. OK. So now we can actually spot where that intercept is. We can actually zoom in a little bit manually and find out that it's around pretty darn close to 40, actually. A little below 40, like 39.95. All right. 39.9455. You can see that there's an answer to where that impact point is, but this is a bit of a pain to do. We'd like to calculate that impact point automatically. All right. How can I find that impact point without doing a zoom in, without doing the plot? How can I get MATLAB to solve that for me explicitly? What do I want to solve mathematically to find the impact point? Yeah?
The intercept of our horizontal line.
Perfect. The intercept of our horizontal line, the ground, with our trajectory. The intercept, how would I write that as an equation? How would I write the intercept as an equation? Set the functions equal, right, set the functions, one of them's equal to 0. I was thinking set it equal to 0, but you're absolutely right. So we've got the two things. We want to find their intersection. So we want y equals 0 and y equals to that long thing there. When we set them equal, we're going to get y naught plus whatever it was, tan theta naught times times x minus 9.8 over 2. Let's put it all down here. 2 v naught squared cos theta naught squared x squared equals 0. You want the impact point? Well, it's where the trajectory, the parabola, fits or hits or encounters the y equals 0 line. Set those two things equal because they're both y values. And we're going to get an equation like this. Is it linear in x? Definitely no. But if you just focus on the x terms, what kind of equation is it? If you had to classify it as something, what would you classify it as? Polynomial, or more specifically even, quadratic. Right. That's why we get that parabolic relationship. So there's bad or nasty coefficients, but if we don't mess with them, it is quadratic in x. Okay. So it's nonlinear. But it's not the, oh my god, it could be anything kind of nonlinear. It's a very well understood family of nonlinear, which is polynomials. Polynomials show up everywhere, and they have nice properties. Nicer properties than the general case. And so it turns out that we can actually get roots of polynomials, because that's what we have here, is we want to find a polynomial equals 0, so the roots of it. We can find roots with MATLAB.